says that with those two regions, each of size n, you say k is the number of ones, k is less than or equal to 1 minus epsilon n. This is all just fitting into the definition. Then with very high probability, in fact, the probability that fails is exponential in the size of the regions. The number of ones that ends up on the wrong side, on the left side, is less than 1/2 times 1 minus epsilon and c minus 1 times n. Again, I'm not going to show you the proof of this lemma, just as a very high level. Mention that the proof involves modeling the C regions, compare exchange operations as a martingale, and then applying the method of bounded average differences to derive this bound. And for those of you that are unfamiliar with this technique, it proves that you have not read Ellie's book, because he describes this technique in his book. So, if you haven't done that, you owe it to yourself. Next weekend, sit down, read that section, enjoy a wonderful weekend with Ellie's book. And then what I do is, in this case, is to show this lemma to deal with the regions that are somewhat close to the mixed region, but not too close. Because what it's showing is that essentially, just by setting epsilon right in the analysis, you get this exponential decrease in the number of ones that are on the wrong side. And then by doing this in this bubbling way, bubble sort way, you get to push all these ones exponentially fast over to the other side. I'm sort of anthropomorphizing this Oblivious algorithm, but at least that's what helps me think about it. Likewise, we also had the second lemma, I call the little region lemma, that shows for C plus 1, 2e to the c, 4e log n leverage splitter. Similar kind of claims here. The proof for this one involves C applications of a Chernoff bound, which you know is also in Ellie's book. If you don't know what that is, you definitely need to sit down this weekend. Read this book. And because he has a whole chapter on this subject, Chernoff bounds. This lemma is used for regions that are relatively far away. The idea is that by having this sort of this floor and saying, okay, the number of ones on the left-hand side is going to be at most either this exponential decreasing, okay, now with this extra constant factor coming in, or it's just going to go below log n and we don't have to worry about it anymore. It's become an extreme region at that point. So this is a way sort of naturally folding in the guys that are becoming extreme regions or are almost extreme regions. And then finally, what I call the slow depletion lemma is that this is dealing with guys who are very close to the mixed region now. So we're just going to let k be less than n minus k, no epsilons anymore. Epsilon is equal to a factor of not just a 0 that's going to be dependent on the epsilons. And this is yet another application, in this case 3 applications of the method of bounded average differences to show that you get this 1/6. So it basically says you get at most 1/6 of the ones end up on the left-hand side, with 3 applications of region comparison. So, getting to your question, Phil, what I show is, as an induction invariant, is that we have this desired dirtiness that we'd like to have after every iteration. So after the iteration d, the desired dirtiness of each region is going to be n over 2 to the j plus d plus 3, where j is your distance from the mixed region. So you have that's literally an exponential decrease in your dirtiness as you go away from the mixed region. And if you're right next door to the mixed region, we'll just make it 5 times 2 to the d. Where again, d is the iteration we're in. So all the regions are of size n over 2 to the d. So this is just a little bit better than what you get from just looking at the size. So what I show is that after iteration d, each region I, the dirtiness of ai is as desired according to the invariant, and that the total dirtiness of all the extreme regions is at most order log squared n. And then you just have to look at each type of region, apply the appropriate lemma each time. This is where it starts to get pretty technical, and so that after you've done, then you do this operation, either scan left, scan right, or the bucket passes, then you're going to have this desired amount of dirtiness Again, it's getting exponentially small, 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 until at the end, everybody is extreme. And there's only polylog amount of dirtiness among all the extreme guys, so now we're in that state of being almost sorted. There's only polylog guys that are out of order. And so then you just apply that post-process and stuff. Just to show you some of the intricacies involved, I'm not going to go over this slide, but just this is one case out of 16 and some of the math involved. I don't think you can do that. I'm not going to go over it anyway. I went ahead and implemented this in Java. It is, like I said, a really simple algorithm. I was trying to see in practice how often would you have to, do the region exchange. Initially, I had set SQL to 4, thinking that's how many region exchanges you'd have to do. This is just the exchange. So this is the only part that's data dependent. Actually, do an exchange. Compare exchange here, based on the values. So if this now becomes your black box, nothing else is data dependent. Just put a random permutation here. This is the compare exchange function. So it just does the random permutation. And in fact, if you comment out this one line in the algorithm, you get a deterministic Shellsort algorithm. So that one line is the only place the randomness is used. And then the whole rest of the code is just going through all those for loops. Shaker pass, bricks of interval 3, 2, evens, odds. Or odds, yeah, odds and evens. That's it. So then I thought, okay, let's just run this and see how big C has to be before it works. And I did C equals 1, and it worked all except for one time when n was 500,000. And I did 10,000 passes at every value of n. So in practice, it just works. So I said, okay, how about if we skip some things? Well, if we don't do the brick pass, well, that brick pass is really important. That already by the time you get to 1,000 elements, you had a 100% failure rate if you didn't do that. Or how about the little short jumps at the end? Again, if you don't do those, it just fails. It doesn't sort. How about the long jumps? So we did jumps of like 3 and jumps of like 2. Well, you can get by for a while just having a few failures if you don't do those. But after a while, it starts to catch up to you, and you start to have failures at that level also. But if you just have C equals 1, so just do one random action between the regions and do those compare exchanges, it almost always sorts. So in the follow-on paper, when we do applications of this to secure multi-party computations, we just set SQL to 1. It runs really, really fast.
This is again without post-processing?
Yeah, no post-processing in practice. Wasn't needed. That was only, in order for me to get that very high probability bound, I had to put in that for the sake of the proof.
But yeah, so have you looked, or your co-author of the next paper, have you looked at
I haven't looked
if
at how
there
you
exists a counterexample? I'm just curious.
No, we haven't looked at that at all.
Could be no counterexample.
Yeah, I don't know. It might be needed. I just couldn't get it in practice already. It was just working, so there's some gap there. Maybe. Another question.
What was the actual bound on this? In other words, if you had had the number of failures predicted by your bound, how many would you
Let's see. So it was 1 over polynomial in n, but now that's with C equals 4. So already at 1,000,000, it would be very, very small. For that case, it would be 1 over n to the 4th failures. So that's like 1 over n to the 12, 10 to the 12, something like that. Another question?
What were the input permutations you used?
Oh, I was just using random permutations here.
Have you tried sorted or anti-sorted? Because it's possible that random instances
In
are represented.
principle, but because the algorithm itself is making random choices, I don't think it would matter. I could code that up tonight and let you know. Send me email. Because I showed you all the code. I mean, that literally was the whole program. Yeah, Steve Rice left, but he's anything less than 1,000 lines is not even a program. That's right. So that was just like, breakfast for him. But I coded it up, and that's a problem. So. All right. So let me conclude then by just summarizing again. I've given a simple, oblivious n log n time algorithm that sorts with very high probability.